Well, the attributes of correlation, again, can range from a negative all the way to a positive. And what that means is if we're looking at a positive relationship between two variables, as one variable increases, so does the other. In inverse, looking at the negative, when we look at two variables, as one variable increases, the other would decrease. And so you can see from this chart that a perfect relationship would be either a negative 1.0 or a positive 1.0. But that seldom happens, so we have a range, and you can see from the range, if we have a coefficient correlation of 0.7, either plus or minus, that's considered a high relationship. Or if we have a negative 1 to a plus, or negative 3 to a plus 3, that would be considered a low relationship. As we measure correlation coefficient, we often do that using a scatter plot, where one variable is on the x axis and the other variable is on the y. And we graph the relationship between the two variables. So the first one is a scatter plot for the correlation between pull-ups and chin-ups. And again, as you visually look at this, you can see that there tends to be a pretty high positive relationship with chin-up scores and pull-up scores. Here's a scatter plot of correlation showing the relationship between body weight and pull-ups. And as you would expect, as body weight increases, the number of pull-up decreases. And so this, again, would be considered a rather high relationship, but in a negative, a minus, because one variable is increasing while the other variable is decreasing. Now here's an example of just a scatter plot that has no or zero relationship. And as you can tell, it's pretty much all over the place. So as we talk about coefficient correlation, we also need to discuss the coefficient of determination, which is just the coefficient relationship squared. And this actually represents the proportion of shared variance between two measures. So you take your correlation coefficient, you square it, and it will give you a percentage or a proportion of the shared variance between the two variables. So in this example, we can see that 19% variation, it's not accounted for by the variable. However, 81% would be accounted for by the variable. So to determine the likelihood or the measure of error between your two variables, you would look at the coefficient of determination. There are some limitations of using Pearson's or the ppm correlation coefficient. One is if the relationship between the two variables is curvilinear, it will underestimate the true relationship between x and y. So the Pearson product movement correlation coefficient really indicates relationship in a linear relationship, not a curvilinear relationship. So an example of that might be looking at arousal level and performance. And as you can see, we do have some relationship. As arousal increases, so does performance. And then you have the optimal level before performance decreases with increased arousal. This would be an example of a curvilinear relationship. And again, using Pearson's coefficient correlation would not predict the true relationship in this example. Another limitation is that correlation does not necessarily indicate a cause-effect relationship. We need to remember that. It just shows that there is a relationship, but there may be another variable that may cause the relationship to be high, or for that R value to be high. So you cannot say from a correlation study that it creates a cause-effect relationship, only that there is a relationship. And then another limitation of correlation coefficient is that it is greatly influenced by the variance or the range of the variables measured. And the guiding principle is the greater the range or variance, the greater the likelihood of relationship. And if the variance or range is small, the less the likelihood of an accurate relationship. And here would be an example of that. You can see with the lower numbers, we show no relationship. But as the range increases, we can see then a positive correlation demonstrated. The second part of this chapter talks about prediction. And once we know the coefficient correlation, we can start predicting. We can estimate the value, or the value of y, say, from an x. That would be a simple correlation. If I know what x is, I can predict, using simple correlation, what y will be. And if I have more than one x variable, then I might use a multiple correlation. Again, being able to estimate the y based on, in this case, a number of x variables. So if x and y are highly related, then x can predict y to some degree, and vice versa. But again, let me remind you that this does not imply a cause-effect relationship. It just implies that there is a relationship. We're not sure what is causing it. Here is a great example of what would be considered a perfect relationship. And we're plotting a straight line here. We do know, as we look at regression, prediction, we will be plotting variables for, in this case, x and y, to see how they fall along the straight line. When we talk about simple linear prediction, we're actually talking about regression. And this is nothing more than a statistical method that's used to predict the criterion outcome, or the dependent variable y, as we look at the predictor or independent variable of x. And we're not going to go into it, but it is listed in the textbook that as we use this prediction equation, it shares the same form as the equation for a straight line that you probably learned sometime in geometry. So this is linear prediction. We also know that we have a standard of error. So this is the statistic that we use that reflects the average amount of error in the process of us predicting y from x. You see the formula there. We also might call this standard error, or sometimes it's referred to as standard error of prediction, SEP. We can also use multiple regression, and as we mentioned before, this is a more complex prediction of y, and we're predicting y based on more than one predictor of x. So we could have x1, x2, we could go on x3, x4, but it's considered a multiple regression because we're making a prediction on y based on more than one variable x. So as we summarize this chapter, it was just a quick overview of correlation and prediction statistics, which lays the foundation and for further measurement and evaluation. And these skills are necessary for generating measurement theory. And then even as we talk about reliability and validity later,